Hey, how's it going? So this is going to be the first episode in about, I guess, a 5-part series. We're going to do the first 4 episodes. This is chapter 1, philosophical mathematics, but we're going to do, I guess, 4 episodes building up mathematics from first principles. And then the last episode, we're going to talk about modern physics. Okay, modern. You could even say postmodern, I guess. Theoretical physics. Okay, I hate using the word postmodern though, but when we think about usually like modern physics, we think like quantum mechanics and all this stuff. But this is going to lead more towards symplectic geometry and kind of more real modern physics, theoretical physics in terms of invariance, representation theory, differential geometry. Okay, but in order to build all of this, we first have to recognize basically a lie that permeates the heart of how we are taught mathematics. There's no such thing as pure mathematics. Okay. We're usually told, and this might trigger a bunch of people, but this is an audience, or I'm trying to gear this towards an audience that is inclusive of pure mathematics. Okay, and so feel free to debate me. But I want to show you that the illusion of pure mathematics is something that is ingrained within us when we separate physics and mathematics. So we're usually taught that math is a view from like nowhere, right? That it exists in some kind of void and it's independent of time, space, or the human mind, right? That's really an illusion because math isn't discovered in the ether, okay? It's constructed. And it is constructed by human brains that evolved in a physical universe. Okay, so first of all, mathematics is constrained by physics and metaphysics, or second order physics, right? For example, if we look at the law of non-contradiction, this isn't just a rule of like grammar, right? It's the assertion that identity must be stable. Okay, universes, or in a universe where it could where objects could simultaneously exist and not exist, where identity is fluid and acausal, logic fails. And the logic is the physics of thought. And like physics, it requires some kind of preconditioning. Okay, so that's the first metaphysical constraint that mathematics operates in. It is not pure. Okay, the second is there's actual physical constraint of mathematics. So if you think about it, the number 1, right, relies on the existence of discrete objects, things that don't merge or vanish when you look at them. And in fact, if you look at the definition, we're going to get into this, but the pure definition of numbers themselves relies on the von Neumann hierarchy. Von Neumann was a physicist, okay? So there's no such thing as pure math, all right? In fact, really the only fundamental things are physics, okay, metaphysics, so physics and second order physics, and philosophy. There's logic, ontology and epistemology, which gives us proof, sets, collections of things, and then arithmetic. That's really where mathematics comes from. Mathematics is generated in terms of our philosophical and physical assumptions. So feel free to debate me on this, by the way. Join the Discord. Let's go at it. I like talking about these things, and I'll promise to have a respectful dialogue, but this is essentially kind of a myth. Okay, there's no such thing as pure mathematics, and in fact, often it's used as kind of a laundering mechanism, which I will get into in later videos. I'm not going to get. I want to focus more so on the concepts themselves. But yeah, objects, right? We can't have a universe that is pure fluid, and everything is like some kind of continuous soup. We would never have invented arithmetic then. 1 relies on the existence of discrete objects and things that don't merge when you vanish, or things that don't merge or vanish when you look at them. Okay, so before you can calculate anything, right, you need to excavate a foundation to build, calculus or physics. Really, to build any of that, you need to first build the idea of the universe. So we're first going to rebuild quantitative reasoning from our 4 pillars here: logic, sets, proof, number. Okay, and before we have numbers or even things, we need a language that can't lie. And by the way, I'm working on developing a website that's going to have all of this for you guys to read through on your own. But feel free to pause whenever you need to, etc. So first, we're going to we don't want to have numbers or ideas of things. We first need a language that's not going to be able to lie. So think about, natural language like English, Spanish, Mandarin, whatever, right? They're really messy. They're poetic in a sense, like, I should have done this or should have done that. Could have, would have. This is very vague, and it's on purpose. Language in and of itself is open to logical, fluidity. But in mathematics, we're going to replace language with propositional logic. Okay, and so we have these ideas called atomic proposition, and these are indivisible statements. That's why they're called atomic. That are assigned binary value, true or false. Okay, 1 and 0. We bind these atoms together using 5 primitive connectives, and they're just defined by truth tables here. Okay, so negation or not P, conjunction P and Q. It requires P and Q, right? So if we look at the conjunction of P and Q, if they're both true, it requires both of them to be true. If both of them aren't true, like you can just go through the table, right? Disjunction, P or Q, right? Implication, P implies Q. And then biconditionality, P if and only if Q, all right? So true gives you true. True, false doesn't work. False gives you true, okay? So really, look at this. This one's the strangest one here. The most dangerous symbol in this new language is the arrow. All right, this arrow is very dangerous because it implies, or the idea of material implication. Material implication is the one that we strictly use in mathematics. All right, and this confuses literally everybody because it doesn't mean cause and effect. It is a material claim. So that means that it only breaks. So it is only false if the premise is true and the conclusion is false. For example, okay, if I say the moon is made of green cheese, then 2 + 2 is 5. That statement is actually true. Why? Because the premise, right, the moon is cheese, is false. And in logic, if you start with a lie, you can claim anything. So logic then is garbage in, garbage out. And it's kind of this machine, right? So it ensures consistency, but not factual reality. That's a really important thing to understand. So we can then derive fundamental equivalences. So implication is disjunction. So the connective here is logically equivalent to not P, right? It is logically equivalent to not P or Q. So if we have P implies Q, that is defined as not P or Q. Okay, and it matches entirely. Next is De Morgan's laws. These allow you to push the negation inside the parentheses. Okay, so if we have not, okay, P and Q, this is defined as not P or not Q. So P and Q, not P or not Q. And if you want to show this computation, let's say the premise is true, and then Q is false, and then if we have P and Q is F. So not P and Q is true. The right side then would give us that not P is false and not Q is true. So not P or not Q is true. These values will match, and this gives us De Morgan's laws. There's also something called semantic consequence and tautologies. So a formula phi, let's call this a formula. Phi is going to be called a tautology. And it's usually written as this like perpendicular equality thingy. Phi is a tautology, okay? And it's true under every possible assignment of true or false to its variables. And these are the absolute truths of propositional logic. So if we write, gamma, right? Some set gamma, right? And then we have the tautology of F, we would write this expression here. If every assignment that makes all formulas in the set gamma true also makes phi true. And so gamma would then be a tautology of phi, or the formula phi. So this gives us some really interesting tools, because everything, again, I don't want you to focus, the main focus of this segment is not objects, right? Not so much gamma or phi. It doesn't really matter what a formula is, what the set is. I just want to show you the logic, right? That's what you want to focus on right now. So if we look at the law of excluded middle, we'll say P or not P. Everything is either true or false, and there's no third state, right? So this is very important, because this then proves, or this then shows us, yeah, there's only true or false. There's no such thing as a third state. Second thing is modus ponens, and it's a tautology. So if P implies Q, and we have P, we must also have Q. All right? This modus ponens. Peirce's law is an application of modus ponens, because if we assume P implies Q, forces P to be true, then P must also be true. All right? So again, we have some configuration of our set, right? All the formulas within the set also makes this true, so we have a tautology. Natural deduction. So this is where we can use proof as a machine, okay? We have a little bit of it, we're getting a little bit of into proof and epistemology, but it's not exactly epistemology yet, because we're just working within this truth table, okay? Or sorry, these truth tables, okay? So that's really all we're pointing to. It's kind of a game. So you can think of truth for small systems, but they start getting, truth gets really, it explodes in size. So to do mathematics, we create a system of inference rules that'll let us to derive conclusions from assumptions without enumerating all truth assignments. So natural deduction gives us an introduction rule and an elimination rule. This tells us how to prove a formula with that connective, and then how to use a formula with that connective. For example, if we have the and introduction, so we say from phi and psi, infer phi and psi, okay? Pretty much. If we do and elimination, we say from phi and psi, infer psi, or sorry, infer phi or psi. You see what I'm saying? So the difference is, if we have from these two things, we can infer we can infer the proof of a formula with that connective. Okay, but if we use the connective, we can infer the status of phi or phi or psi. You see, kind of, there's a little bit of an asymmetry happening here when you introduce or eliminate something. Implication introduction is the same thing, right? You can, if you assume, this is typically what we use in physics. If we assume phi, you can derive psi. Then you may conclude phi implies psi and discharge some assumption. Okay. Also, you can do elimination, and this gives us an application of modus ponens, where we have phi implies psi, and phi allows us to infer psi. Okay. So of course we assume the formula first, and then we try to get information out of it. That's the elimination. Okay. And then not introduction. So assume this, and then you can derive a contradiction. So this is a little bit of proof, right? But I'm just showing the power of the logic and using logic in and of itself statically. All right. So let's prove Peirce's law. I'm going to show you how we can use modus ponens. So assume the left-hand side, okay, and then use a reductio ad absurdum argument. Okay. So if we assume not P and derive a contradiction, we can conclude P. So assume first that P implies Q, which implies, oh well, hold on. Sorry. P implies Q, which implies P, right? Assume not P, right? For contradiction. We want to assume a contradiction. And then we'll also assume P as a temporary assumption. From 2 and 3, we can obtain that contradiction, right? And that's what we'll denote as this perpendicular thingy, okay? From 3 and 4, we can infer, right? P implies Q from a contradiction, any Q follows, all right? This is kind of the subtle thing that we're talking about with just the universe, right? In which, you have something false, right? And then the implication really only allows you to propagate the truth value of it if for any Q that follows, right? So from 1 to 5 here, by implies elimination, we can infer P, and then from 2 and 6 here, we can obtain another contradiction. From 2 and 7, we can infer not P, okay, and then by double negation elimination, we conclude P. This allows us to discharge the initial assumption in 1, right? And this allows us to then prove by contradiction, okay, or by reductio ad absurdum. This illustrates how proofs in natural deduction mirror the informal reasoning mathematicians usually perform, but it's got to formally, we can formally check this structure, right, in terms of doing all of this. But instead, mathematicians, we tend to abbreviate our logic, okay, by using introduction and elimination for proof. Predicate logic. Now, you can think of this as like meta logic, right? Where if we have propositional logic, it's very like coarse, right? We have all of these things. So X is prime, right? This would be like a single atom, right, that you can't look inside. So what we want to do is internalize or try to analyze the internal structure of the statements. So we'll need something called predicate logic. Define something called a domain of discourse. This is the universe of objects that we're talking about, okay? And we can then define quantifiers, okay? So universal quantifiers and existential quantifiers start to come to play. So if we have the formula, right, for all x, that gives us a formula of x. It's true, right? If phi of a is true, or the formula of a, right, is true for every object a in the domain of discourse. Okay. The existential, and this domain of discourse is not abstract. It's a very it's a computational thing. So if we also have an existential quantifier, okay, there exists an x, right? The formula, there exists x, right, for phi of x, that is for it to be true. It's only if phi of a is true for at least one object a in D. Okay, at least one object. There's also some variations on there exist with the exclamation mark. This just tells you that there is a unique object, okay? But this one just says at least one object. So you can think of this kind of like as a, then again, we get more into meta logic, but this is important, okay? Predicate logic is where we will start. So quantifier negation. So pushing logic through things. So if we want to negate a quantified statement, we can flip the quantifier and negate the predicate. So if we say not, there exists some phi, right, of x, we can equivalently represent this as there exists some x not in phi of x. And you can do the same thing here. Not, there's an inherent symmetry between both of these definitions. So not, there exists x, right, of phi of x, some formula of x, then there exists x, right, that's not on the formula of x. So you really only need to think about the truth value of these and flipping the quantifiers so that you can negate the predicate itself, right? So, for example, we can translate language into, or English into these kinds of statements here, okay? So translating these basic things into more of a precise language. So every mother loves some child of hers, right? So for all, and we say we have a formula, right, for mother, right? That's a formula of x, okay? Mother of x implies that there exists some y with child of, right, of y of x, where x is the mother, right? And loves x comma y. So for any person x, if x is a mother, then there exists some y such that y is her child and she loves y. Okay? This requires this shows you that, of course, you can take the English language and get very precise logical readings, and this is something that you really have to practice, okay? This would be an example of an incorrect formalization. There is one specific superchild y that every mother loves, and this basically, your quantifier, the way that you're ordering the quantifier is not consistent with pushing the logic through. So, for example, if you have case 2, no prime is even except 2. The logical form of that is for all x, right, the prime of x, and x is not equal to 2 implies it's not even, right? So, and then another one is a student passes only if they pass the final. And the logical form of that is for all students, right, or for all x that are students, right, and they pass the course, this implies that they pass the final. Here, only if expresses a necessary condition, which appears on the right side of the arrow. Okay? Now let's talk about language now, because we talked about, okay, why do we need to do all of this? What is the point of all of this? What is semantically being, quantified, and why do we need to be precise with this? Because this formalism or this symbolism, and we can demonstrate this with Russell's problem of denoting, which he showed in 1905. Natural language cannot reliably handle existence and reference. So if we consider the sentence here, the present king of France is bald. Okay, the present king of France is bald. Is this true or false? Okay, if you ask if this is true or false. Obviously, it depends, right, on what this is trying to convey. Because if you read this, that there exists exactly one present king of France, and that person is bald, formally, you can see there exists, king of France, and the person is bald, But since there's no present king of France, the statement is false. Do you see what I'm saying? So the statement is false because there's no present king of France. France is I think it's a democracy. Okay. Another informal reading. Okay, if we look at the existence condition and focus only on the conditional structure, for any person x, if x is the king of France, then x is bald. So formally, we can have here that the king of France is false for every x, and the implication is vacuously true for every x, and the universal statement is true. So we can get true and false depending on how we choose to phrase it. So natural language will obscure this distinction, and logic forces us to decide what exactly we are asserting. Do you see the power of why we need logic? Logic is very important because we need to know what we are asserting. Otherwise, there's no point in doing any of it, okay? In terms of creating some kind of mathematics or whatever. So now we can describe this as something called the grammar of truth. We can speak about objects with precision using connectives and quantifiers, okay? But we still face a deeper problem. We haven't really created the objects themselves, right? So we have predicates, but really no subjects. And what we need to do now is create the idea of objects. So what we need to do, just needed a drink. We need to invent the concept of a thing, okay? What is a thing? Well, in math, we can just say a set, okay? But here's where early mathematicians almost broke the universe, okay? Well, but before we get into this, we want to describe two complementary foundations. There's something called ZFC and ETCS. We're not going to get too much into this, but I think this is where a good foundation is, and then you can know about category of sets, and this will come back later in our physics investigation. But, so what we need to do is forge the concept of a thing and build them safely. There's a whole minefield that almost destroyed math. So there's something called Russell's paradox, okay? And if we naively allow unrestricted comprehension, sounds kind of abstract, but basically says if you define the set of all sets that do not contain themselves, let's say R, does R contain itself? And you can have two different cases of this. R contains itself, and by the definition of R, any element of R must not contain itself. Hence, R is not an R, and you get a contradiction. Okay, so this is kind of a thing you need to avoid. And then in the other case, assume R is not an R. Well, then R satisfies the defining property of membership in R, so R is in R, and you also get a contradiction. Okay, so in other words, the set of all sets that do not contain themselves. Do you see what I'm saying? This is a contradiction, and in both cases, we're forced into R and R if and only if R is not an R and the universe collapses. Okay, so any serious foundation has to block Russell's paradox. Okay, but also it cannot be so restrictive that the even number 2 cannot be constructed. You see what I'm saying? So what we do is we say, okay, Zermelo-Frankel set theory with choice. This is really the go-to. This is typically what's taught in any mathematics class. So again, if the set contains itself, if this set contains itself, it shouldn't. If it doesn't, it must, and it's a logical bomb. If we allow this, 1 can equal 0, math collapses. So what we do is we introduce these rules or axioms. And you can think of ZFC as kind of the safety regulation so that we can avoid this, all right? So here's all the axioms, all right? Extensionality, this means that a set has no hidden structure beyond its elements. So there exists a set A and B, right, for all x of stuff in A, if and only if the stuff in B, for all x, if they're both parts of the same set, then those sets are equivalent, all right? And this is called extensionality. If two sets have exactly the same numbers, they're the same set. It's essentially what we have. The next axiom is the empty set. This means that there exists a container with nothing in it, and this is the seed of the universe, denoted the null set or the empty set, okay? So there exists some A, right, for all x that's not an A. And so anything that is not in the set, right, anything that is not within that set is the empty set, okay? There exists a set that contains the empty set, and it is closed under successor operation. And we'll define this a little bit later. But this guarantees an infinite sequence, and we'll come back to this, but the convenient formulation postulates that there's a set omega, right? So there's a set, the empty set is in omega, right? And there exists, for all in omega, that in is the union of the set of in, and they're all in, and they're all within the set of omega, okay? This one's a little more abstract, we'll get to it. Axioms of constructions, they just say you can make new sets from old ones. Pairing, this means if you have any two objects, A and B, we can create the set that contains exactly them. So if you have for all A and for all B, there exists C, okay? For all things that are within C, if and only if x is equal to A or x is equal to B, okay? So this allows us to pair, or from any two objects, right, we can create the set that contains exactly them, all right? Next is the idea of union. So we'll say given a set of sets, we can smash them together and collect all their elements into one big set. So if we have, there exists some A, right? Oh, sorry, for all A, there exists a B, right? For all the things within B, if and only if there exists some Y, where Y is in A, and X is in Y, okay? So this allows us to then make a union of the set, okay? This is an axiom. The next axiom is power set. This means for any set, the set of all its subsets denoted as math calligraphy of P, or sorry, math calligraphy P of A, right? This is some kind of operation, right? The power set. I keep doing that, sorry. What we can do is describe the primary way that the universe grows in size. So if we have, there exists some A, right? Or sorry, for all A, there exists some P, right? Where all the things in P, if and only if X is a subset of A, where X as a subset of A abbreviates this idea. So a subset, X being a subset of A, is really always just shorthand for there exists some things in X, right, that imply that those things are in A. Okay, it's almost like kind of like a transitivity thing. Not necessarily transitivity, because that's more arithmetic, but this is more so like just the implication, right, that if there's something in X, right, if something in X, then that's also a part of A, right, a subset. Now, the axiom of restriction. These axioms prevent paradoxes like Russell's by carefully controlling comprehension. I didn't put exactly everything in there. It's not the most important one, but it's one that's, again, you can look all of the ZFC axioms on this. I'm just trying to go through an intuitive description of this. So for separation, we may only carve subsets inside of an existing set. So for any formula phi, and let's say you have X and then P1, Pk, in any existing set already, there exists a subset, okay? X, the stuff in A, right? Given the formula for X and then P, Pk, whatever, right? These are other things. There exists some set for all A, and for all of these Pk, right? All this formula depends on these other things. There exists some B set, right? For all the things in B, if and only if, okay? If and only if X in A, and there is a formula that depends on the things in B, and then also these other things. Well, then this gives us something called Russell's monster, and Russell's monster of A is equivalent to the set of all the things in A, where X is not equal to X. This is probably the more subtle one to understand, but we need an axiom of separation so that we can carve subsets inside of an existing set, depending on what is within A. Okay, so the B allows us to carve this for all the things in A and the rest of these things. The rest of the stuff, the formula depends on the P1 to Pk. This is a harmless subset of A rather than a universe-destroying object. Okay, so we essentially avoid Russell's paradox, and this is how we do it with Russell's monster. The next one is foundation and regularity. So every non-empty set A contains an element that is disjoint from A. So what that means is, for all A, where A is not the empty set, this implies, right, that there exists some X within A, the things that are within A, and the intersection, or the intersection of the objects, right, with the set of A that is equal to the empty set. So what the consequences of this is that no set can contain itself, which means that X within X is impossible, and there are no infinite membership cycles. So, X naught, X1, X2, X naught again, okay? So that's what the foundation or regularity gives us. This one I would walk through as well. This is a very important one. The replacement axiom, again, there's no way to prove these things. These are just axioms that we're holding, okay, to construct mathematics. Or it's essentially set theory, which then constructs numbers in mathematics, okay? Replacement. If phi of x, y, p, all the way to pk acts like a function on A, for every x in A, there exists some unique y with phi of x and y and p1, pk. The image of this, right, so let's say y such that the set of y such that there exists some stuff in A with the formula, this would also be a set. Okay? So this acts like a function on A. Okay? And formally, if there exists things in Y, then there exists one unique Y that corresponds to the formula for x, y, and then all of these other things P1 to Pk. Then there exists some B such that for all the stuff within B, for all the stuff within B, exists if and only if there exists stuff in A that depends on the image. Okay, or I'm sorry, not the image, but it depends on the unique Y within phi. All right, so that is the axiom of replacement. And the last one is a more interesting one. It's called the axiom of choice. So for any A of a non-empty pairwise disjoint set, there exists a choice set such that if we do the intersection of the choice with some x, okay, and the cardinality of that intersection is 1. The cardinality of that intersection, we're just saying it equals 1 for each thing, or for each object within any set of non-empty pairwise disjoint sets. Okay? It's a little abstract, but the meaning of that is from each non-empty bin, right, x in A, we can pick one element, even if no explicit rule is given, and this axiom is essential for modern analysis. So, this allows us to have, of course, we can pick we can choose a basis, essentially, for vector spaces, or, but it's not a constructive axiom, okay? So this is the axiom of choice allows us to have vector spaces, linear algebra, Hilbert spaces, function spaces, everything, okay? Tensor spaces, whatever. We can choose bases. We can choose whatever we want. We can choose our coordinate system. Okay, that's the axiom of choice. If we have a trajectory, right, of some parabola, we throw an object or a football. We don't have to choose, a particular coordinate system where it's like 3-dimensional and we want the trajectory. We can just choose the plane that describes the trajectory. You know what I'm saying? And we can just use that coordinate system. That's essentially the way to think about this. Okay. The cumulative hierarchy. Now that we have ZFC, okay, which is all this shit, which is kind of a lot, but now what we can do is describe that there's a tower that can be built in stages indexed by something we will define as ordinals, alpha. So let's say we have v sub 0 to be equivalent to the empty set, okay? And the ordinals we will define as v of alpha plus 1 is the power set of v of alpha, okay? So if we want to go to the next one over, we will do a power set operation on some v of alpha, v sub alpha, okay? To get alpha plus 1. So there's something called a limit ordinal, which basically says for some beta less than lambda, we're just going to union all of these, v sub betas, which are just typically they're sets, right? And the full set theoretic universe that we can construct from, some set, right? So some set V would be described as the universe, would be just the union of all the ordinals, or the union of over all of the ordinals, okay? And then, of course, this is how we define limit ordinals. Some placements, to place things within this hierarchy, we can say, well, here's the null set, which is in V1, okay? And since V1 is a power set of V0, V1 would be the set of the null set, okay? And then if we have the set of the null set is in V2, then we can have the set of the null set, which gives us V3. And this is what we call a finite von Neumann natural number, okay? Or natural in, right? We don't have an idea of a number yet, but we're getting this primitive definition of a number. It's called a finite von Neumann natural. And it lies within V of n plus 1, or V sub n plus 1. Omega then will lie in V omega plus 1, and the power set of omega lies in V of omega plus 2, okay? V sub omega plus 2. So that means that every valid set appears at some finite or transfinite stage within this hierarchy, and if it does not appear in any V sub alpha, it just simply doesn't exist, okay? And this is good because now we can construct numbers. We can use VFC to build the natural numbers from the null set, from the empty set. So von Neumann ordinals just means that every natural number is the set of smaller natural numbers. That's it. Every natural number is the set of all smaller natural numbers. So if we have 0 is the null set, and then 1 is the set of 0, which is the set of the null set, or the empty set. And then we have 2 is just the set 0 and 1, which is just the set of the empty set and the set of the empty set again, okay? And we can keep constructing this over and over and over. And in general, we can define something called the successor of n, which gives us n, right? And the union of its set, right? And so the successor of n will then allow us, the set of all natural numbers denoted omega can be shown to exist inside of an infinite set provided by something called the infinity axiom. Okay, so I told you guys we're going to come back to this. This just means that if there's a set that contains the empty set and it's closed under the successor operation, so that's what this is. This is a successor operation. So X, we're doing a successor, and it's closed under this. This guarantees an infinite sequence, 0, 1, 2, 3, 4, 5. And it postulates a set omega such that if there's some empty set in omega, and for all in omega, there's in union the set of n within omega. That's the infinity, okay? The infinite generation of integers, or of numbers, okay? So because numbers are sets, we can perform operations on them. So of course, the intersection of 2 and 3 would be what? The set of 0 and 1, the intersection of set of 0, 1, 2, 1 and 2, and then which would then give us, if we do the intersection of this, the thing that 3 and 2 have in common is 2, okay? By using this definition from our von Neumann hierarchy. Next is membership. So also 1 is in 3. And that's true because 1 is an element of 3. Okay? Because it contains a set. The set 3 contains a set within it. Okay? The subset also is true. It's also a subset. So not only is it a set, it is a subset of 3. So numbers, both as sizes and as structured sets, is a very, very important insight to understand. Okay. Next are the idea of order, functions, and coding. So sets are inherently unordered. If you have A comma B to be B comma A, inherently that's true. But to do geometry or physics, you need ordered data, like coordinates, okay? Where position matters because that'll tell you like exactly, something on a Cartesian coordinate system or on a curved geometric space, something like that. So you need some kind of order. Now what we do is we do this weird thing where we say, okay, we want the set of A and the set of A comma B. What this does is this set actually behaves like an ordered pair, and we can show this. So there's a way to prove this. If you have A comma B is equal to C comma D, then they have this. They're forced to have the same elements, and the singleton, which is the set of A, right? It just contains one object within it. It must equal one of the elements on the right, so A equals C. And then if you look at the doubleton, this A equals C forces B to equal to D. So thus, A comma B is equal to C comma D implies there's an implication that A equals C and B equals D. And this is called faithful coding, okay? We can define something called ordered triples and longer tuples recursively. So if we have this ordered triple here, A comma B comma C, this should be equivalent to A comma, and then recursively defining it B and C in an ordered way, right? And this gives us longer tuples. Functions are sets. So in set theory, we can define a function really as just a graph, okay? A function in set theory is a graph. So we'd say this process here, this isn't implies anymore. It's now A is an arrow to B. It's a set really of ordered pairs. So if you look at A cross B, okay, the product of these two sets, if the function itself will be a subset of this, product of these two sets. So that means that there exists there exist things in A where there is, I'm sorry. It should be for all things in A, okay? Erase everything I just said. For all things in A, there exists one unique Y in B, okay? where we have ordered pairs that are in the function itself. So the ordered pairs are defining the function, but it's unique. So for each input, there's a unique output with y with ordered pairs in f. So in f itself, the function itself is a set. So in pure set theory, a function is nothing more and nothing less than its graph. Okay? Now, let's look at the structural mirror of this. This is called the elementary theory of the category of sets. And this was invented by Lovere, which characterizes sets by its structural properties. So some differences to keep in mind. Instead of building a universe V from the bottom up using objects and sets, right? Objects that are contained within sets. Objects themselves will play the roles of sets, okay? Arrows then will play or morphisms will play the role of functions, okay? They play the role of this. So elements of an object S are arrows 1 to S from a terminal object 1. Okay? So the axioms of ETCS, we kind of went over a lot of the ZFC axioms, but I just kind of want to show you that usually, I'm going to briefly go over them, that the terminal object 1 for every object has a unique map to 1, because it's a function, right? Binary products without projections and their universal property. You can actually exponentiate the sets, so there's function sets, and this gives Cartesian closed structure, finite limits and co-limits, including equalizers, sub-object classifier 2, which encodes subsets via characteristic maps, so we can map, we can then map the objects, right, or the elements of an object S to 2. And also natural numbers object omega with 0 and its successor satisfying Peano's universal property. A form of choice is also ensured that every epimorphism splits. So essentially what we just did was derive an equiconsistent formalism of the category of sets, okay? And what this allows us to do is do geometry, physics, and other things to give us the same working universe of sets and functions, where we have one that's element based and then we have one that's structure based. Okay, so both have their own benefits, but essentially ETCS is ontologically neutral, which means that we can we're not having to assume anything about the objects within the sets themselves, but we get it in more of a structuralism, more of a structural way. So let's look again at the paradoxes, right, that we had to avoid. One is Russell's paradox. Again, we blocked it by the separation axiom. In the absence of a universal set as a member of anything, we can only form that things in A given phi of x for some existing A, and that's what we form, okay? So we're not making any assumptions that would allow us to be destroyed, that would allow our universe to be destroyed by Russell's paradox, okay? We essentially avoid it by doing this. Next is the infinite descent paradox, remember? So if we just want x is an x, x1 is an x2 is an x3, which is an x0, right? We can block this by foundation. Again, this was one of the more confusing ones, but important ones to work through or think about, which is that every non-empty set has an element disjoint from it, ruling out self-membership and membership cycles. That's essentially what we're trying to do. And then the last thing is the set of all sets, right? This was blocked by hierarchy. So the full universe, again, is a proper class. It's not a set, okay? So we can't contain the universe. We generate the universe as a proper class, but it's not a set, okay? So the universe is not a set. It is too large, really, to be an element of anything. So the monsters, again, are not cured, right? But they're just non-existent within the theory. So these things don't exist. We just avoid them, okay? If ETCS reaches the same safety it's going to reach it from the opposite direction by looking at only the structural behaviors that are consistent with a time universe. And again, giving us the ontological neutrality that we think is interesting. So, the void is no longer empty. It contains the empty set, and from the empty set we built 1, and from 1 we built omega. From omega we have power sets, products, function spaces, and we can build real numbers, manifolds, and Hilbert spaces. So if you think in terms of elements or arrows, you now have the raw materials of mathematics. And what this allows us to do is encode virtually any structure in modern science. But what we still lack in a disciplined way is to extract truth from these structures. Okay, we talked a little bit about these things here. I guess like some basic proof methods in logic, but we were really just focusing on the logic. Let's talk more about the epistemology of proof in mathematics. All right. So a proof, it's not an argument. Okay. A proof is not really persuasion either. There's no rhetoric involved in epistemology. It is in and of itself a data structure. In other words, it's like a chain, right, of iron links where the first link holds and the last link must also hold. You can think of this as like, I don't know, like a blockchain. If you guys are familiar with like Bitcoin or like mining, right? When you prove something, essentially you're not making an argument or whatever. It's just encoded within the data. So really, what a proof is, it's a checkable data structure. Okay? So every formula, every chain of formulas, or the formula that's a chain of previous things from axioms gamma, is an axiom. It's either an axiom of the theory, is a member of the parent set or the premise set, or it is obtained from strictly earlier lines of phi sub j with j is less than I by a valid inference rule. Nothing else counts. So if you have like, diagrams, drawings, it seems obvious, you can't do that, okay, at the formal level, okay? If the chain breaks at one link, the theorem is not proved, okay? Now, this doesn't mean you should never do this. Intuition is pretty important, but then again, intuition will lead you astray if you're not confined within the axioms of the theory, the truth tables, and if you're not doing this full method of modern proof. Okay, so let's look at this. We have really 4 atomic weapons of rigor in mathematics. There's really only 4. There's direct proof. You can just assume P and then using definitions and theorems derive Q. And then you just write P implies Q. Okay, this is the default. Okay, this is what like 90% of everything is. There's also contrapositive. There's reductio ad absurdum, or proof by contradiction. And then there's mathematical induction. So there's really the 4 atomic weapons that we have. Let's look at this. So the contrapositive just says that if P implies Q, you can equivalently have not Q implies not P. And you can just, if you prove one, you get the other one for free. Because their truth tables are equivalent. I mean, that's basically how it is. So if n squared is even, then n is even. You can just say if n is odd, then n squared is odd. Okay, so we're just reversing it. And then, because there's only even and odd, right? And then since the contrapositive is true, the original statement is true. Okay, and then you just prove it. You can prove phi, right? By assuming not phi. And then you can derive an explicit contradiction, or symbolically you would call this, again, that perpendicular thingy. And that just means it's a contradiction. So if logic itself is not allowed to break, so the assumption not phi must be false, so that phi is true. Okay? So let's say, for example, square root of 2 is irrational, right? How do we know it's irrational? We assume it's rational, okay? And then we assume that it's a neat fraction. And then we just grind kind of the assumption through, until it like spits out a contradiction. And numbers must both be even and odd at the same time, and that can't happen. So since logic can't break, our assumption must be false. So square root of 2 can't be a fraction. Hopefully that makes sense. And there's also the infinitely many primes. This is also done with contradiction. Again, this is showing you that you can propagate theorems that are already known, right? You can just use them and then arrive at a contradiction. Just follow the premise. Here's kind of another one. Mathematical induction. To prove a property P of n holds for all natural numbers. This is a very powerful, this one's not used as much, but it's very powerful because typically you have to hypothesize some kind of form. That's why it's like really hard to come up with these ideas. And this typically happens like, by, I don't know, like God revealing to you or something, the formula, or just having some kind of weird, like intuitive way of finding it. So that's why this one's not as used as much, but when you get it, it's like, wow, they're very famous proofs. So for example, the sum of, integers, we just do 1 plus 2 plus 3 plus 4, whatever. There's an explicit form for that. And, somebody just came up with this, and then they're like, I mean, you can think of a geometric argument for this, like draw the squares or whatever, cut it in half. But at the end of the day, because what is this? This is like an area, right? And then you divide it by 2 to get the sum. So of course you can think about it, right? And this again, it goes back to the whole, of course, intuition diagrams, physical plausibility seems obvious. Again, we're forbidding this this is forbidden at a formal level, but like we can show it again when you prove something, right? You can use this. God can give you some, I guess, like insight, right? Oh, the universe is expanding or something. Georges Lemaitre. And he's like, Einstein, the universe isn't isotropic because I said so, or because God told me, So, but of course, all you have to do to prove something is to make sure that the chain doesn't break, and then you can prove something. So this is exactly what you can do, as long as you prove the chain doesn't break for the first couple of integers. So you first start with n equals 1, okay? Well, the sum of I to 1 is just 1, right? So 1 plus 1 plus 1 divided by 2 is 1. They match. And then you can do an inductive step towards this. And you can arrive at, oh my gosh, the formula holds, for all in, for the k plus 1 case. And so that's all you have to do to prove. So again, let's go back to our idea of natural deduction. For our conjunction, our disjunction, our implication, not, for all, and existence. This allows us to then use the introduction and elimination tables to prove things. Okay. Again, we mentioned this for each logical symbol, but this allows us to use both cases for to kind of condense the degrees of freedom in which we're doing all of these propositions and everything, and propagating the truth value from the truth tables. So again, we can also consider this example where we have some arbitrary, just like, P implies Q and R implies S, and P or R implies Q or S. Okay, so you can just compute this. I mean, have fun. We can also look at the drinker's paradox. This one's a little more interesting. So for all x, right, we have P and that has x, and this implies that there exists, or that for all y, P is in y, P of y, assuming that the domain is not empty. So with this drinker's paradox, the reason it's called the drinker's paradox basically means that there's someone in the pub such that if they're drinking, everybody is drinking. You see what I'm saying? So like, you can work classically. So using contradictions and vacuous truth, you can assume not that there doesn't exist this. Okay, so assume this, and then you want to push the negation inward. So just symbolically going through this, rewriting the implication again from the rules that we derived earlier, or that we showed earlier. And then we just negate the disjunction and pick an arbitrary element of the non-empty domain, and we can have some P of A and not there isn't something for all, P and Y. And then so if P of A holds and also this holds, a fully natural deduction proof will unwind these assumptions and will allow you to then get the desired existence statement. I'm not going to go through the whole thing, but this is basically, it shows you it's structural, right? That the statements here, they sound paradoxical, but they can be resolved cleanly within a precise proof system. So yeah, there is someone in the pub such that if they're drinking, everyone is drinking. That sounds really like counterintuitive, right? But this is really important because the logic will allow us to have the rigor that's needed so that we don't have to just rely on intuition to just we don't have to rely on God giving us formulas for things, right? To understand the truth value, okay? And guess things. So essentially this allows us to, this creates kind of a little bit of a tension, but they're not really tensions. They're more so complements of each other. But there is this divide, philosophically, of what counts as valid proof. If you look at the classical Hilbert logic, he accepts the law of excluded middle, which means that if we have P or not P and a double negation elimination, that's universally valid. So you can prove the existence by contradiction by showing that there isn't, or not, right? So there's not some, there exists some X in the formula for X, and that leads to a contradiction, okay, without producing an explicit example. So you don't have to make a counterexample or whatever. There's a constructive intuitionist logic that does not accept this for arbitrary P. So to prove A or B, you must actually prove A or actually prove B to prove then that there exists some X within phi. You must also exhibit such an X. So most of analysis in modern mathematics is developed within, of course, Hilbert, right? Within Hilbert's classical framework. And this relies on non-constructive results. So for example, the spectral theorem or whatever will exist. There is some eigenvalues without telling us how to find them, okay? In this idea, or in this series, we're going to work classically, but there are some non-constructive principles, especially excluded middle and choice. They're doing some real work as well. So this is just something to keep in mind. There's also constructive and intuitionless logic. Now, there's a limit to everything. Even with these tools of epistemology, or of mathematical epistemology, or epistemological mathematics, we hit a wall. And Kurt's Gödel proved that no matter how good our system is, and this is really kind of a slap in the face, but there will always be truths that we cannot prove. This is just a matter of the physics of the assumptions that we have made within the frameworks of ZFC or anything, any form of system at all. Okay, it doesn't matter what you construct. There are blind spots in the very thing that we forged, but for the math we need, the tools are really enough. Okay, so of course the forged proof is inherently limited. No single computable system can capture all arithmetic truths. But that's okay. This is enough, okay? For the math that we need, it's enough. And for the math that, mathematicians need, or the math that engineers or physicists need, this is enough for us. But now that we hold really, the key ring, right, of the chains of proof, right? Every theorem you will prove in analysis, geometry, physics, whatever, we're just using these basic strategies, just direct proof, contrapositive, contradiction, and induction. Maybe some case analysis, okay? But, then again, induction and case analysis, these all come from our set theory axioms and the logic that embeds everything, okay? So, really, as you can see, in mathematics, epistemology and logic are really coupled together, but ontology is kind of its own beast, okay? And we formalize really everything with natural deduction. So Gödel again showed that all truths can't really be opened by a single finite system. But theorems are the ones that we really need, right? So we don't need all the truths. We just need the theorems to have everything within our reach and construct exactly the goal of mathematics. Okay, so Now we can build 0, 1, 2 from nothing. All right? But sets and proof. So again, what we have here is this alchemy. Okay. We're going to turn nothing into something we will coin, or something that's coined the continuum. All right. So start with the empty set. Okay. Start with the empty set, and we'll call that 0. And then we'll take the set containing the empty set and call that 1 again. And then, the set with the empty set and then the set of the empty set is 2. Okay. And then we'll literally build counting numbers out of empty boxes inside empty boxes. Okay, so just a bunch of empty stuff. And then successor, of course, you remember that n plus 1 will be equivalent to n and the union of the set of n. Okay, recursively. And we're going to denote the smallest of such set is denoted as omega. And we identify omega with the natural numbers. Okay, that's great. But embedding Peano arithmetic inside ZFT, we need to build the integers, which handle subtraction. And we also need to build the rationals. So we build the integers here. And naturals form something called a monoid. Under addition, it's not a group. Whereas we can have order that's defined by membership. Again, addition is defined recursively. Everything's defined in terms of sets, okay, in ZFT. Monoids, we can add, but we cannot always subtract. So 3 plus x is equal to 1 has no solution in the natural numbers, right? But we can construct negative numbers as an equivalent classes of pairs of naturals. So we have 5, 3, which represents 2. 1 and 2, 100, which represents 2. So when we recognize equivalence classes of pairs of naturals, so intuitively we can represent the difference, or the net difference in the pairs, we can formally define something called an equivalence relation on the natural numbers across the natural numbers, okay? By just saying that a comma b has an equivalence relation with c comma d if and only if a plus d is equal to b plus c. So then we can then define the set of integers as just a set of equivalence classes of the ordered pair a to b, a and b. We can then have operations like the 0. Like 0 would be defined as this equivalence class, okay? The set of all the equivalence classes essentially would just be, there's one unique 0, right? Then the additive inverse, which would be the negative of the set of all the equivalence classes whenever you flip it over. So you just change the ordering. And then the addition, right? Which will then give us the a plus c and b plus d as we impose over here. And guess what? One can check that these definitions don't depend on the choice of representatives, and that the integers, okay, with the additive as an additive group, they are abelian, which just means that you can reverse them and you get the same thing. So we can solve equations like, x plus 5 equals 2 by just saying x equals negative 3. Next, what we do is, in the integers we can subtract, but we can't always divide. So, 2x equals 1 has no solution in the set of all equivalence classes of those ordered pairs for the natural numbers, okay? So what we do, of course, remember, this is quotiented by the equivalence relation, okay? So we can construct fractions as equivalence classes of integer pairs with non-zero denominator. So with b, so if we have a pair, right, with b is not equal to 0, and it represents the fraction a over b, this can represent, 1/2. This also represents 1/2, though. We can formally define this as, let's say, the set x, right, where a comma b are in the integers, integer across integer, given that b is not equal to 0. Define an equivalence relation on x as such if and only if a times d is equal to b times c. then only we can make a quotient space of the rational numbers by the set of this ordered pair, given that b is not equal to 0, and that's the set of rational numbers. So for these equivalent classes that are in the rationals, we then define addition and multiplication and such. Again, these operations are well defined on equivalence classes, and in this inherited order, the rational numbers become something called an ordered field. And in this stage, right, the reason it's an ordered field is because one of the particular, the b cannot equal to 0, okay? So at this stage, numerical universe seems kind of complete, right? Like we've completed everything. But it turns out there's holes in this equivalence class. Why? Well, the ancient Greeks actually believed the rationals were enough for geometry. But there's no rational number such that q squared is equal to 2. So suppose there exists some q, or some little q, in the rational numbers. Okay, and the rational number, when you square it, gives 2. Write q is equal to p over r in the lowest terms, where these are both integers, and their greatest common denominator is 1. Okay? Guess what? Then when you propagate the proof of this, you basically find, essentially, that, if you walk along the number line of fractions, you will fall into the gap where the square root of 2 should be. You see what I'm saying? So the sequence here, it marches towards a limit, right? But that does not exist in the rational numbers itself. So, of course, and we would have to prove this by contradiction. You can follow the steps. But since r squared is even, so r is even, and both are even, and this contradicts the assumption that p and r are in this lowest term. So there's no rational solution to this equation. All right. So what we have to do is use Dedekind cuts. We take a knife and we slice through the rational line, right? And the cut itself is the space between the fractions, and that becomes a new number. So because we're necessitating that a continuum needs to exist, what we're going to do is partition the rationals into two non-empty sets such that, the set A and set B are not the empty set. Every element of A is less than every element of B, and A has no largest element. So intuitively, a cut represents the position on the number line where all rationals left are in A, are all to the right and possibly at the cut are in B. Okay? So the real numbers R are then defined as the set of all of the Dedekind cuts. Okay? So let's say we have a rational cut at 2. A is for some element of the rational numbers, okay, such that q is less than 2. All right, so we're creating the first rational cut, so this is our first one. The second set here, B, we're going to say that it's for some element in the rationals, given that q is greater than or equal to 2. We're cutting it, and this cut corresponds to the rational number 2. The irrational cut at square root of 2, we can define it as such, except where we have q is less than 0 or the q squared is less than 2. And then we have q is greater than 0 and q squared is greater than 2. This cut here has no rational boundary point. So that means there's no element in q with q squared is equal to 2. So the cut in and of itself is the real number is the real number square root 2. Okay? This is kind of subtle, but it's basically the space between the fractions becomes that new number. All right? So by filling every single gap, right? Every single gap is filled by this definition of a Dedekind cut. Remember, it's a partition of two non-empty sets. Okay, they're non-empty. And basically everything, when we fill it in, that's the real number. So we have gone from the empty set now to essentially the real numbers. Now, there's also something, there's a very important concept called completeness and topology of the real numbers. The power of the real numbers, okay, defined by the sealed, or that it's sealed by a cut, and that each cut is a precise set of rationals. The power of this is that it's complete. So there's something called the least upper bound property, that every non-empty subset, okay, of the real numbers is bounded above, has a least upper bound, or a supremum, on the real numbers. So in the Dedekind cut picture, the supremum is represented by essentially taking the union of the lower halves of the cuts, okay, supremum of the lower halves of the cuts corresponding to the elements of S, which again forms a valid cut. And this property is what makes calculus possible. So in the limits of Cauchy sequences, infinite sums, continuous functions, they all rely on the existence of such least upper bounds. Topologically, the real number line is something called connected. That means it cannot be decomposed into two disjoint, non-empty open sets. Also, the real numbers are also uncountable. So if you can look up Cantor's diagonal argument, this basically means that there are strictly more real numbers than rationals. So the rationals are dense, right? But they form a dust. The reals are on the solid lines. So we have essentially gone from, in this video, we've gone from the empty set to the infinite continuum. And we didn't discover this line, we forged it. Okay, we built it from logic, sets, and proof. And now that we have kind of built the stage, we can finally begin to describe things. And we are truly ready for analysis. Okay, so we now have an unbroken line from negative infinity to positive infinity. And so essentially we've turned, again, the empty set into the real numbers using nothing but logic, sets, ontology, and proof, epistemology.